Let's look at section 11.1, the fundamental counting principle. We're going to learn all about this. You may remember this from middle school or high school. So let's go ahead and get right into it. So the definition, you can choose one item from a group of m items and a second item from a group of n items. Then the total number of items is m times n. You can make a tree diagram. So here's an example of choices of making an outfit. We have 2 pants and 3 shirts. 2 pants, 3 shirts. So you want to find out how many total outfits you can make with 2 pants and 3 shirts. So you could make a tree diagram. So you can either pick um, the blue ones or the black ones. And then you could also pick a gray, a white, or a black t-shirt. So here's a tree diagram to list out all the outcomes. So it's blue pants with white shirt, blue pants with gray shirt, blue pants with black shirt, black pants with gray shirt, black pants with white shirt, black pants with black shirt. So this lists out 1, 2, 3, 4, 5, 6 outcomes, 6 different outfits. So you can always make a tree diagram. That's what this is, listing them all out. Or you can use the fundamental accounting principle of multiplying the outcomes. So 2 times 3 equals 6. So it's the same thing. This is just listing them out using the tree diagram. Let's look at the next example. The Greasy Spoon restaurant offers 6 appetizers and 14 main courses. How many ways can a person order a 2-course meal? So you could list them out, all your appetizers, and then 14 branches off of each of those, or you can just multiply it. Using your calculator, you should get 84. So 84 2-course meals. So you're listing all possible outcomes. And let's look at the fundamental accounting principle with more than 2 groups of items. So this is pants, shirts, and shoes. So it says we have 2 pairs of jeans, 3 shirts, and 2 pairs of sneakers. So you can count them up if you make your tree diagram: 2, 4, 6, 8, 10, 12. Or you can know that you can just multiply all possible outcomes times each other. So you have jeans, how many jeans, times how many shirts, times how many shoes. So we have 2 jeans, 3 shirts, 2 shoes. Multiply that together. 2 times 3 is 6. 6 times 2 is 12. 12 different outfits. Here's another example. You're taking 3 courses. You have a math, an English, and a humanities. There are 8 sections of math, 5 of English, 4 of humanities that are suitable. Assuming no schedule conflicts, how many different 3-course schedules are possible? So you would do the same thing. There are 8 choices for math, 5 choices for English, 4 for humanities. So we're going to multiply 8 times 5 times 4. So I would do 8 times 5 is 40. 40 times 4 is 160. So there are 160 different 3-course schedules. Shoppers in a large shopping mall are categorized as male or female, over 50, 49 to 30, and 29 and under, and cash or credit shoppers. And how many ways can the shoppers be categorized? Okay, so we have the gender is the first. So we have male or female. Then we have age bracket. So over 40, 49 to 30, 29 and under. So we have 3. And then our last one is type of payments. And then our payment. So there are cash or credit. So there's 2. So 3 times 2 is 6. 6 times 2 is 12. So 12 different ways shoppers can be categorized. Another order. All right, let's look at example 4, multiple choice test. So you're taking a multiple choice test that has 10 questions. Each question has 4 answer choices with 1 correct answer per question. If you select one of these four choices for each question, leave nothing blank. And how many ways can you answer the questions? So you have 10 total questions, four choices for each. So you're going to do the same thing as what we've done in the past, which is multiply the 4 times the 4 times the 4, all the way till you get to 10. So 4 times 4 times 4 times, I don't want to write all that out. I'm going to do it like that. And then I can represent it like this 10 times. Well, if you think back to how we represent that with exponents, we would do 4 raised to the 10th power. So in our calculator, that's what we 4 raised to the 10th. So you do the little caret top for the exponents, right? So 1,448,576 different ways you can answer the questions. Let me turn the page. In a different plan for area codes, the first digit can be any number 1 through 5. Second digit was either 7 or 8. The third digit could be any number except 4, 7, and 8. With this plan, how many different area codes are possible? All right, so we have 3 digits, right? We have the first digit, the second digit, and the third digit. All right, so the first digit can be any number 1 through 5. So 1, 2, 3, 4, 5. So it can be one of 5 options. And we're going to do the same thing, multiply. Second can be either 7 or 8. So we have 2. The third can be any digit except for 4, 7, and 8. So you do need to remember that 0 is included in this. So 0, 1, 2, 3, so not 4, 5, 6, not 7, not 8, 9. So that's 1, 2, 3, 4, 5, 6, 7. So you multiply these. 5 times 2 is 10. 10 times 7 is 70. License plates. We can also look at how many ways that license plates can be done. So 4 letters followed by 3 numbers. So 1, 2, 3, 4. So these are all the letters. And then followed by 3 numbers. These are all the letters. These are all the numbers. Okay. So let's think about how many outcomes are there for letters. Let's more A, B, C, oh, there's actually 26 if you remember that. So we're going to do 26, 26, 26, 26. And then numbers, we have 0 through 9. So that's a total of 10. You could list this out a little easier with exponents. So it's 26 to the 1, 2, 3, 4 times 10 to the 1, 2, 3. Now it'll make it a little easier to put in the calculator. Okay, we have one last example. A stock can go up, go down, or stay unchanged. How many possible are there if you own 5 stocks? Okay, so we have 1, 2, 3, 4, 5. Okay, how many outcomes do we have for a stock? What are the outcomes? Go up, go down, stay unchanged. There are 3 outcomes. Each stock has those same 3 outcomes. We're going to multiply these. We can do 3 raised to the 5th. 243. 243 possible outcomes. course, you want them all to go up, right? All right. Y'all have a good